Good morning, ladies and gents. Welcome to the third lecture here in Organic Chemistry 1. It's the last lecture of the week. It'll be a short one since we covered so much information in the last 2 days. And also what that means then is that you're going to have an exam on Friday, tomorrow. It's going to be posting at 8 o'clock in the morning, and you have until 11:59 p.m. to take the exam. It will be remotely proctored by Proctorio. And I think most of you know already how Proctorio works, but just in case you didn't, it's going to have a webcam. You're going to have a webcam, and you're going to have a microphone on while you're taking the exam, so that Proctorio can do remote proctoring. And you just can't do too much, suspicious behavior and stuff, right? That being said, you are allowed to use a piece of paper for scratch paper, and you are allowed to use a periodic table. Just make sure you show the camera that stuff before you start the exam. So that we can see it, the Proctorio can see it, that you just have a periodic table and a blank sheet of paper. Also, make sure you bring your ID with you, your identification, driver's license, school ID, or whatever. It doesn't matter. Show it to the camera as well, so that we know you are actually the person that's taking the exam. You are you, and then also just be very careful, right? Try not to do anything suspicious while you're being recorded or being remotely proctored during the exam. All this is being done so that you can take the exam the convenience of your own home, right? On your own personal computer. Absolutely do not click out of the window that the Proctorio exam is on, because if you click out of the exam, you will be kicked out of the exam. If you click out of the exam, that means you will be kicked at. Okay, one more time. If you click out of the exam window and try to look at anything else, right, then you will be kicked out of the exam. And I'll tell you right now that once you get kicked out of an exam, there's nothing I can do to get you back into the exam. So make sure that doesn't happen to you. That's why you have a scratch piece of paper you can use, and you have a periodic table, a printed hard copy periodic table, because you're not going to be able to go back and forth between the exam and then another window that has a periodic table you can use. So just make sure you're clear on that. Also, your first assignment and quiz were due earlier today, so I hope everybody got that stuff submitted on time. And also your lab, your first lab exercise was also due, right? I believe it was due actually last night, right? Yes, at the end of the day last night. That's right, Wednesday night. So I hope everybody got all that stuff submitted as well. I've noticed already that there are a few students that have not even signed on and registered for LabFlow yet. Make sure you sign on for LabFlow. There's like 4 people left that have not signed in for LabFlow. And just know that if you don't sign in for LabFlow, register for LabFlow and you do your lab, you will not be getting credit for this course, because you have to take the lab to get credit for this course. And then also I saw several of you have already registered for Wiley Plus. That's good, because the videos that I'm referencing during my lectures are super helpful. They supplement what I'm lecturing to you and give you practice problems with somebody working them for you. It's David Klein. He's my unofficial organic chemistry hero. So make sure you subscribe or register rather for Wiley Plus. All right, so that's it for the announcements for this morning. I wasn't planning on doing all these announcements this morning, but I guess all this stuff just came out. So let's go ahead and get started. We'll do lecture 3 today, which is our last lecture before the Friday exam. And let me change the view real quick here so that you can see the presentation. Okay, so let's go ahead and get started with lecture 3, molecular representations, and sorry, my head's blocking again, but that says resonance. There we go, resonance. All right, so what exactly is resonance? Well, I want you to take a look at this allele carbocation right here, right? And you notice that when we draw this allele carbocation here, we have a double bond there, or a pi bond there, and a plus charge there for the carbocation part, right? So when we draw these line angle structures, and just so you're aware and remember, when I say line angle, I'm using that synonymously, interchangeably with bond line structure. And I guess maybe bond line would be more accurate, because They're not all angles in this thing. Maybe they are though, because I was just thinking about the SP hybridized carbon, the one with the triple bond, like this. And I was like, maybe that's true. Maybe it is just bond line, but no, that is a 180-degree angle, right? So maybe me calling a line angle drawing isn't so wrong after all. So I'm gonna keep on doing that. Anyway, back to the topic at hand. Um, when we draw these line angle drawings, we assume that where we draw the double bond is right here, or that where we draw that double bond is, the pi bond is, we assume that that's where those p electrons, those pi bond electrons actually are, like they're stationary or stuck right there on that side of the atom. Turns out that's not actually true. When you take a look at this closer, especially through the lens of the molecular orbital theory, remember that when you have two p orbitals that overlap, they form a bonding molecular orbital, right? They also form a anti-bonding molecular orbital too. So that's important, but that's not really what we need to talk about here, because when it forms the bonding molecular orbital, we know that this bonding molecular orbital actually spans the entire length of the molecule, right? It spans the entire length of the molecule. So really, those pi bond electrons, right? They're not stuck right there, just on the left side of the atom, where that we draw the line, right? So really, these line angle drawings, they inadequately, right, describe where those electrons are. They very inadequately describe where electrons are, and in fact, they are actually more spread out, right? And the word we'll get to is called delocalization. Okay, delocalization, which is actually right here. It's just being blocked by my head. Delocalization, right? Pi bond is also delocalized between carbon 2 and 3 as well, not just 1 and 2. So let's take a look at what I'm talking about. So remember that the sigma bonds between these carbons right here, right, and these hydrogens here are all sp2 hybridized, right? They're sp2 hybridized from the sp2 hybridized to form the sigma bond, right? And when we did that hybridization, being sp2, we left over one p orbital, right? That wasn't hybridized, right? If it was sp3, then all three would be hybridized. But we have to leave one out of it, right? So that we can form the pi bond, because sp2 hybridized orbitals cannot form a pi bond, right? They only form sigma bonds. So the leftover p orbital is what forms the pi bond. And those p orbitals are these orbitals right here, right? And notice that these p orbitals, they overlap each other, right? They overlap each other. It's not just here that they overlap, where we see that we draw a double bond, or a pi bond, but in fact it overlaps over here too, right? So based on that, the electrons are actually delocalized through the entire area of electron distribution where these molecular orbitals actually are overlapping, right? Again, that's why drawing something like this is inadequate, because it makes it look like the electrons are only just on one side, the left side of the molecule, right? But in fact, they should be distributed throughout the molecule, okay? Again, that's called delocalization of the electrons. Just to put what I just said in pictures here, right? Those three overlapping p orbitals, right, form the bonding molecular orbital here, right? And when they do that, you see that all this pi orbital here from the three p orbitals actually does span the entire T of the molecule, right? And so pi electrons can float in between and all around in that area that the molecular orbital occupies, right? To take this a step even further, is that we already know that whenever two P's come together to make an MO, you also get a bonding MO. You also get an anti-bonding MO, right? But in this case, there's also a non-bonding MO, and the non-bonding MO shows electron density on both sides, right? But these are empty shells, right? Which is what the +1 denotes, right? The +1 or the +1 charge. Oops, sorry. What the plus charge right here, the carbocation denotes, right? It's saying that for these non-bonding right here, whatever it's saying, that this plus charge here is actually missing electrons. It's an empty orbital, non-bonding, but when you draw them out, the non-bonding orbitals symmetrically, right? There are actually on both sides. These empty orbitals are on both sides of the molecule, not just on the right side of the molecule, like this drawing shows here with just a carbocation on the right side. So what that means then is that this plus sign should also be on the right side too, to reflect this non-bonding MO being empty as well. So how do we put that all together, right? How do we put that all together into a line angle drawing that makes sense to us? This is how we do it. They're called resonance structures, okay? Resonance structures. We have the original one here where the carbocation is on the right and the pi bond is on the left, but it can switch back and forth, right, between that and a structure where the double bond is on the right and then the carbocation is on the left, right? Does that make sense? Having the bond on both sides in this resonance structure, right, over here and over here, on both sides of this resonance structure, the left and the right, reflects the overlapping p orbitals, right? They're of the molecular of the bonding molecular orbitals, and then having the plus sign or the carbocation on both sides, the left and the right, in this resonance structure, reflects the fact that the non-bonding molecular orbitals, right, that are empty, are on both sides of the molecule too. If that makes any sense. And we'll get to this in much more detail later. But you can see, and I alluded to this in a previous lecture before, whenever you have a carbocation there, right, that's an electron sink, right? It's a positive charge, so electrons can go there, right? So remember when you draw an arrow with the two-sided arrow, you can draw a two-sided arrow showing that this bond goes over here, right, to form a double bond over there, leaving behind the carbocation, another carbocation over there, right? And forming this new double bond over here, right? On this side. And then you can draw the arrow again to go back to that one. And now you're going back and forth between the two. Now, when we draw a resonance structure like this, right? Now it looks like it's either one or the other, right? Or it's switching back and forth between the two, like really fast, and we just don't know, right? But in fact, the real representation of this molecule right here, this allele carbocation structure here, is it's somewhere in between. It's somewhere in between, okay? Oh, I skipped ahead. So, when we have the two resonance contributors, right, which are the things that we just saw a second ago, right? The one with the pi bond on the left side of the molecule, the carbocation on the right, and its other partner there, which is the carbocation on the right, and the double bond on the carbocation on the left, and the double bond on the right. Those are called the resonance contributors, right? But you can also draw what we call a resonance hybrid, where it shows something in between, like I was just saying in the last slide here, where this double bond here represents, this dotted double bond here represents the double bond being somewhere in between the left and the right carbons, right? And then also showing that there is a delta positive or partial positive on both of these carbons, because it's somewhere in between, right? It's somewhere in between. And if you look at this resonance hybrid right here, right? You look at this resonance hybrid really does reflect or show what it looks like to have those bonding molecular orbitals overlapping, right? Because now you have electrons going back, filling that entire area there. But then, and then I'll try to draw the bottom one too. Oh, that's terrible. But then that's the red side is on the top and the blue side is on the bottom, right? The other phase, the opposite phase. But then It also shows, the resonance hybrid shows really well the non-bonding orbital, right? Molecular orbital, where we had them, right, on either side. Empty p orbitals on either side, right? Or empty molecular orbitals on either side, which denote the carbocation, right? I'm sorry my structures are so bad there. Just let me just back up real quick. Those things right here, these things, right? They say you need to be a really good like artist to be a chemist, right? But let me tell you right now, the vast majority of the time, where you're in organic chemistry or whatever, you're drawing hexagons. It's always hexagons. Or I guess in this case, phenyls. Or benzene rings. I haven't drawn so many hexagons in my life, ever, as much as I did when I was in organic chemistry. The class you're in right now. Which wasn't so far off from me, so long ago for me. Sorry, let's keep going. So, the point of all of this, though, is that when you have resonance occur, you have electrons spreading out over or delocalizing over a much larger area because the molecular orbital is much larger than the singular p orbitals that you had before. And so when you do that, that actually reduces energy, right? It actually stabilizes the molecule, right? Because those electrons that are bouncing around don't have to be so confined anymore, right? In addition to that, too, you also delocalize the charge, right? And when you delocalize the charge, that also stabilizes the molecule, right? So the point of this here is that resonance stabilizes the molecule, right? Because it gives those electrons space to move around, it minimizes repulsion, then more freedom, greater distance, and all that fun stuff, right? And then also it delocalizes the charge, right? And all of this together results in a much more stable molecule. And here we have our resonance hybrid. Of our previous example. So I've already skipped ahead before here, but I guess we're going to go ahead and introduce it again here, the curved arrows thing, right? So I said the thing I drew the most in organic chemistry was benzene rings, right, or hexagons with double bonds inside. I guess the second most drawn thing in organic chemistry when you're a sophomore are curved arrows, okay? And curved arrows denote or demonstrate electron movement. Electrons moving from one atom to another atom, okay? And so this arrow has two parts, a tail and a head, just like any other arrow, right? But the thing I want you to know here that it doesn't say here is that you can actually draw an arrow that has one head and an arrow that has two heads, like that, right? I don't know, two feather, no, the feather's on the other side. No, okay, you can draw an arrow that has one of those things, and then you can draw an arrow that has two of those things, right? And when you draw an arrow, a normal arrow that has two, sides of the head, right? That means you're moving two electrons, okay? And then when you have an arrow that when you draw only one side of the head, that means you're moving only one electron, okay? For now, we'll be using the double-sided or the double-headed arrow right here, right? The most, because we'll be moving electrons in pairs. But later on in the semester, we'll start moving things in single electrons, and it'll be like, radical. Put a pin in that. Okay, so, like I was showing you before, in the previous example, because somehow I always skip ahead in things, right? When you have a double bond here, and you have a carbocation here, you can draw a resonance structure, right, for that. And how do you know what the resonance structure looks like? You just use arrows to push electrons where they need to go. And remember what I said. The rule is, my general rule of thumb is, electrons are negative, right? So they want to be drawn, or they want to go to things that are positive. Guess what's positive? A carbocation is positive. Why? Because it's got a plus sign right there, right? So you're always, and those are also known as electron sinks. So you're always going to move electrons towards electron sinks, right? You never want to move them anywhere else but to electron sinks. So with this double-headed arrow, you can show that that double bond is going there, right? And then the resonance structure that comes from that, right, is going to be, first draw this guy here, okay? And then the double bond just moved there. So the plus sign is gone now on that carbocation, because that carbocation has got its full octet now with the double bond there. But oh my gosh, what happened? I don't have a, remember what happened? Remember in Gen Chem when you said you had to have a conservation of charge on both sides of a reaction? Oh, well that's because now that you've pulled the electrons in this double bond away from that far left carbon over there, carbon number 1, that far left carbon is now a carbocation, right? And that's your resonance structures, or we call them resonance contributors, right? Resonance contributors. You could also do it with the resonance hybrid too, where you draw it like this, right? Actually, no. I didn't even draw it right. Here we go. Let me do this here. There we go. There we go. Okay, we draw it like that, right? And then we can do the double dotted line. Not the double dotted line, but the double bond that's a dotted line, like that, right? And then we can do a partial or delta positive on both, right? Some people actually even do it this way, where they draw it like this, right? With the, like that, right? And then they'll put a plus sign in the middle with a circle around it. But not for that carbon right there, right? It's denoting that where that plus sign is for the delocalization of the charge, right? With that double bond and the dotted line. Cool stuff, cool stuff. So there's some rules when it comes to curved arrows, right? When you draw curved arrows. So let's go through these rules one by one. And as long as you follow these rules, I think that my rule is probably the most important, right? Which is electrons always go towards electron sinks or positively charged atoms, right? But let's go through these official rules real quick, okay? Rule number 1, never show a sigma bond being delocalized, right? Okay, so this is actually curved arrows, movement of electrons in resonance structures, okay? And so when you're drawing a resonance structure, you're not changing the molecule, its structure at all, right? You're just representing the molecule more accurately with a resonance structure. And so we have a carbocation right there, right? And one might think you could draw a double arrow and move that double bond towards that carbocation like I did in the last example. But you can't do that, right? Why can't you do that? Because when you do that, you break a bond. And when you break a bond, that's actually a chemical reaction where you form new products. You're not representing the same molecule more accurately. So definitely don't ever in a resonance structure break a sigma bond. Okay? Never do that. That's bad. Bad. Next, rule 2. Never exceed an octet for a second row element, right? So boron, carbon, nitrogen, oxygen, fluorine, right? They should all have their octets, okay? Like they're either a full octet of 8 electrons in their valence shell or less than that, but they cannot exceed that. You'll see later on in life, though, that sulfur is in a third row, right? It's the same column, right, or period as oxygen, 6A, but it's in the third row, not the second row, and so it can actually have an expanded octet. That's like the exception to the rule when you have things that are below, right, the second row. But if you are a second row element, right, you cannot expand more than 8, right? 4 orbitals and a max of 8 electrons, okay? So if you take a look at this right here, this is a bad arrow. And the reason why this is a bad arrow is that if you move this lone pair here on this oxygen down to this carbon right here, right, you're giving that carbon 5 bonds. What I say in the last couple lectures, that's bad. Don't do that. Don't be like that guy that was in my class a few years ago who was like, I asked him, how many bonds can carbon have? And he said 12 or 6 or something, right? It's only 4, okay? It's a very special carbon that can have more than 4 bonds. We call that a hypervalent carbon, but at this point in your life, Only 4 bonds to carbon. Okay, only 4 bonds to carbon. Okay, this is also a bad arrow here too. Why? This lone pair coming down here puts a bond there on that nitrogen, and now you have more than what? 8 electrons, right? You got 10 electrons there now. That's bad, right? That's bad. Okay. Same thing here, right? Move that down there, bad arrow, because now you have what? 10 electrons again. 10 electrons is bad, right? And then again, right here, that's a bad arrow, right? No pi bond there to move, nothing. That's bad, right? Because remember, when you do that, there's also a hydrogen here. Remember that absent any charge or any other notation, what's there? When there are not all 4 carbon bonds there, they're hydrogens. So that's actually what that looks like. So when you actually move a lone pair of electrons from that oxygen down here to form a double bond there with that carbon, you've given that carbon 5 bonds. No. Don't do that. No. Bad. Don't do that. Okay? 4 bonds only to carbon. Don't violate rule 2. Okay? Somehow I always jump ahead. Anyway, so this is a continuation of second rule here. The second row elements will sometimes have less than an octet, just not more than an octet. I said that earlier, right? And so the one time you can do this here, right? Notice that there is a charge there now on that carbon, right? It's a positive charge. It's a carbocation, right? So remember what I said in the previous slide. Absent any charge or any other notation, you always assume that that carbon has hydrogens on it, right? If there are no other bonds connected to it. And that means it's fully, all of its octets, it's fully satisfied its octet, right? But notice right here, right? There is a charge there, which means it's a carbocation, right? And if it's a carbocation, that means that it's missing electrons. It can get some more to fill its octet. So this minus charge can come back down here and then reform this double bond that's right there. Right? Makes sense? Makes sense. More formal charge stuff. Okay, so let's take a look at this little resonance structure here, or this structure here, and figure out what the formal charges are once you've done a resonance structure or resonance contributor. Because remember, when you move electrons around to do a resonance contributor or structure, it leaves different formal charges now on each of the atoms that you've pulled electrons away from. So the structure that we're going to end up with this here is going to be this. That's what you're going to end up in, right? But what's missing? What's missing is... Oh, I messed up here, actually. There shouldn't be that there. Let me just erase this and do it again. Got ahead of myself. Oops. There it goes. So the structure that we end up here is this. Okay. That's the resonance structure or contributor that we end up with the arrows that are shown right here. This lone pair comes down here, right, forming that double bond right there. And then this, when this double bond forms, right, that double bond forms, you've now got a hypervalent carbon right there at the center. And so that's why this double bond has to move somewhere, and it moves there. But the problem is that what I've drawn isn't complete because it doesn't show what the formal charge is now. And this carbon right here looks like it's just a regular old carbon, right? But in fact, since I've taken a pair of electrons from the oxygen to form this double bond, right, this oxygen now is positively charged, right, as far as the formal charge goes, okay? And then now, this carbon here, right, that's actually a carb anion now, because it has an extra pair of electrons, or an extra electron rather, from the double bond right here that moved into it. That makes sense? Right? Does that make sense? And you might be asking yourself, why didn't we violate any octet rule there? Because this was a double bond that moved, right? That was a double bond that moved. It wasn't a single bond. And then we formed like more single bonds on top of it, a double bond on top of a single bond, right? So let me draw this out a little bit more clearly for you here. The structure for that question mark, all right? Let me go ahead and, do that. Is this. Okay? That's what that structure should look like, okay? All right. Next. Oh, I drew it out, but it's here too, right? So the structure I drew is right there, okay? Actually, the only thing I didn't do was draw the lone pairs on it, which you need to draw the lone pairs on it. But when you get super good at it and you see that there's a negative charge there, you know that there's only one lone pair on that negative charge for that carbo anion right there. And then when you draw a positively charged oxygen, you know that there's only a lone pair there too, because it wouldn't be positively charged. It only had one lone pair. No, oxygen with two lone pairs and two bonds is neutral, right? So these are kind of things that as you practice, you remember, and you don't have to actually draw over and over and over again, right? Because if you look over here, I just drew this positive charge here, but I just forgot to draw the lone pair right there, right? But I knew it was there because it was positively charged. You'll get that good too, right? Again here, a carbanion always has a single lone pair there. Forgot to draw it, but if you drew it the way I did, I would accept that because I know that you know that those lone pairs are there. Just make sure that you know how many lone pairs are actually there, right? So, just like I did in the previous slide, they're showing you the structure here without the formal charges there. So what are the formal charges now after you've drawn this contributor, this resonance contributor, right? Positive charge on the oxygen, right? Because it's lost some electrons to this double bond right here. And then negative charge on the carbon, making a carbanion because it gained an electron from the double bond that went there, right? Quick plug, practice, Skill Builder 2.6, assigning formal charges on Wiley Plus. It's a good time, right? Good time with David Klein. Does that rhyme? Damn, all three of those words sort of rhyme. God, I'm so good. I'm so good. I wish my girlfriend were here to hear me freestyle with you guys. That was just amazing. I cracked myself up. Anyway, there are 5 patterns of recognition, They're resonance pattern recognition. There are 5 patterns that you should look at notice when you're actually looking at a structure to see if it's capable of doing resonance or if its electrons are actually delocalized, right? We'll go through each one of these one by one, right? But the first one is a allylic lone pair. The second one is an allylic carbocation. The lone pair of an electron is adjacent to a carbocation. A pi bond between 2 atoms of different electronegativities. That's kind of like an oxygen and a carbon, right? Because carbon has a vastly different electronegativity than oxygen, right? Oh, and I should probably also tell you too that the word allylic right here, it just means next door. Like the carbon next to the carbon with the lone pair. Or the carbon next to the carbon, that's a carbocation. And then last but not least, it's a conjugated pi bond. Or in a ring or something like that. So I'm always talking about drawing the hexagons, right? And this right here, when you have every other bond is a double bond, that's called a conjugated pi bond. And those can do resonance like that, right? And so the other resonance contributor then is this. Good stuff, right? And it can go back and forth between the two. Oh, no, it doesn't go back and forth between the two. It is actually somewhere in between the two, right? Next. So, let's talk about the very first pattern, right? A couple of vocabulary words here to take a look at. We have the word vanillic and the word allylic. or allyl, right? Vinylic positions, right, are the actual carbon itself. Okay, the actual central carbon itself. Whereas allylic positions are the carbons that are next door to the carbon, the central carbon, right? And so, and my head's blocking something here. Let me go ahead and close my head out real quick here so you can see the whole thing. There we go. So when you look at a molecule like this one, this guy here, those are not allylic electrons, allylic lone pairs, right? Because the carbon next to it, right, is not a double bond. Doesn't have a double bond on it. But when you look at this allylic lone pair right here, it does have a double bond next door, right? This lone pair is on this nitrogen, and next door to it is a carbon that contains a double bond, and that's what we call allylic, right? And if you see that, it's possible, if you see that kind of that pattern on a molecule, it's possible that molecule where that allylic position is, excuse me, a lone pair is, can participate in, I almost said hydrogen bonding, can participate in resonance or delocalization. Let me bring myself back here. Okay, let's take a look at the next one. Right? Oh, sorry, more examples of allylic, right? So all of these right here are examples of allylic. We have a lone pair next door to a carbon with a double bond. Here we have lone pairs next door to a carbon with a double bond. Here is another lone pair, right, next door to a carbon with a double bond. Lone pair next to a nitrogen with a carbon with a double bond, right? And then another lone pair here next to a carbon with a double bond, right? And so, those all, as I said before, can participate in resonance delocalization, right? Resonance delocalization, right? We have these lone pairs here going here, and then you'll have the other structure of this one being this, right? And then here, the other structure of this one will be that, right? And the other structure of this one will be, the other resonance contributor to this one will be not that. Let me draw that again. There we go. Yep. And then the other resonance contributor to this one will be I don't know why I drew I don't usually draw lone pairs, but you're supposed to. Like I said, when you get really good at it, you don't really have to worry about them so much anymore. Like that, right? And then the resonance structure for this one, I've run out of room here, so I'll draw it up here. The other resonance structure for this one will be this. Like that. Right? Just like that. Okay. Cool stuff, cool stuff. Oh, I forgot to draw the charge there. 4 bonded nitrogen. So the other thing you notice too, like whenever you're drawing a resonance structure or the resonance structure of a molecule, and or its resonance contributor, you always have a conservation of charge, right? Where this first one had a negative charge total, and so does the second one. This first one had 0 charge total, and this one also, the second one here, has 0 charge because a minus and a plus cancel out, right? Same thing here, 0 charge total, minus right here, plus right there, 0 charge, right? And then same thing here. We had forgot to do something here. I didn't finish this one, did I? Oh, I drew that one wrong. It's terrible. Let me draw that again. Let's see here. You see, that's another thing too. If you suddenly notice that when you're drawing resonance structures and the charges don't match up, right? You drew something wrong. Okay, and I just noticed I did something wrong there. Okay, there we go. Okay. Okay. And then nitrogen here. And then there. And then there. There we go. That's what it looks like. Because now it has two lone pairs over here. Right? There we go. Okay. Makes sense. Makes sense. That's a good way of checking yourself when you're doing resonance structures and suddenly the charges don't match up on both sides. Okay? Conservation of charge. That's like the first law of thermodynamics or something like that. Something like that. Okay. Wow, there's a lot of practice here. Unless that was just something I did already before. Hold on one second. I lost my train of thought here. Didn't we already do an example of this? Okay. Well, I guess we're just recognizing pattern 1 again, right? Double bonds right next to a lone pair. A lone pair right next to a double bond, which is allylic. Here's another allylic here. We drew the answer to that one over there, right? That's the one I messed up right here, right? That's the one I messed up. But I fixed it because I noticed, right, that there was a different charge from the first and the second one that was there, that was drawn, okay? And then these two again here, these two again here. Those are all done by me on the previous slide. And I didn't know that they had actually done them on the second slide. So, you have my answers on both. You have answers on both. Another plug here. Wiley Plus 2.18. Practice. Okay, so here's pattern 2. Pattern 2 is the allylic carbocations. What that means is that there's a carbocation right next to a carbon that has a double bond, that's participating in a double bond, right? And that was actually one of the very first example of resonance that we were talking about before. Okay, so that can also, since we already drew this, or this person here in the whoever drew this diagram already drew that arrow there, we can also draw this arrow backwards to reform the other one, right? Because we know that it's actually, these resonance structures contribute to something in between, right? I always have to think for a minute when I draw a delta, because you know you're used to deltas being like triangles. That's the uppercase version of delta, the Greek letter. But when we're talking about partial charges, partial charges are denoted by the lowercase version of delta, which is that weird S-looking thing. So yes, that's delta. Okay. If there are multiple double bonds conjugated, like I showed you in that benzene ring, then multiple contributors are possible, and they are drawn by moving one electron pair at a time, right? So we go from here to here to that carbocation there, means then that it leaves behind the carbocation there, which you can see there. This double bond here can move there now, because now that's the allylic carbocation, right? And that leaves now behind a carbocation there, which you see here, and then we can go backwards, right? To go back to the other one. But we know that the actual structure, the resonance hybrid, is something in between. Again, a plug, right? Wiley Plus, go check out 219. Okay? Check out 219. Pattern 3, a lone pair adjacent to a carbocation, right? We've seen this again too before, where we have a carbocation right there, and then a lone pair from this negatively charged oxygen comes down to form a double bond, and now we have the neutral, the carbonyl. Sorry, the carbonyl there. Actually, this is it's a carbonyl, yes, but it's also known as a ketone. Just a reminder of your functional groups. It all comes together, guys. All comes together. Remember it all. Okay. Remember it all. Okay. So here we go. We have another one here, a carbocation right next to a lone pair, right? And so this lone pair comes down to fill that double bond there, leaving behind a positively charged oxygen, right, and a double bond there, right? Notice again, both of these resonance structures, one positive charge, net positive on both sides, right? Notice here, net no charge, right, on both sides. All right, net no charge on both sides. And then, again, another plug for Wiley Plus. Check out 2.2. Okay. In pattern 4, we're looking for a pi bond between atoms with different electronegativity. Okay. And you can actually see that all these overlap, right? Because a second ago we were looking at a lone pair next to a carbocation, and that's what this is right here, right? So they literally overlap, and this is the pi bond next to an atoms of different electronegativity. So these rules actually build on each other and they overlap each other. So it's really hard to get them wrong if you remember what the rules are, because one will cover the other. Do that, and then do the whole thing with me saying the electrons go to electron sinks thing, right? And make sure that the charges are all the same on both sides, and you've got this down. Okay. Again, so since we have rule 3 over here, we can just make this go back down, right? We just make that go back down, and there we go. There we go. Okay. Good stuff. Good stuff. And then number 5, conjugated pi bonds in a ring. I just showed you this earlier, where we have a benzene ring, right? Also known as a phenyl. Right, a phenyl ring, right? Oh yeah, I was like phenyl, right? Because I was thinking about phenol, and a phenol is just a phenol. Except it has an OH on it, right? It has hydroxyl on it. So the same thing as that, except it has an OH. We'll see a lot of those later on in life too. Anyway, so I showed this to you before. We can draw the arrows again to move them back to where they were going before, right? But remember, it's actually something in between the Wiley Plus plug. Check it out, 2.24. So, just to help you out, here is a nice little summary chart, right, of all 5 patterns. We have a lone pair that is next to allylic. Sorry, a lone pair, an allylic lone pair, right? Which means a lone pair next to a double bond, right? A lone pair that's next to a carbon that has a double bond, right? And that usually involves 2 arrows, right? 2 curved arrows to draw the other resonance contributor. Then we have the allylic carbocation, which is the carbocation right next to a carbon that has a double bond. That's 1 curved arrow to draw its contributor, other contributor. We have a lone pair adjacent to the carbocation, right? So that sounds exactly what it sounds like. You know, you have a lone pair next door to a carbon that has a carbocation. That's a single curved arrow. Then you have a pi bond between 2 electronegatively different atoms right here. So we have the oxygen that is vastly electronegatively different than the carbon, right? So that requires a single arrow to show its resonance structure. And then we have the conjugated double bonds like we do in a benzene ring. Okay, and benzene rings are not the only molecules that are conjugated and what we're going to call later on in life too, aromatic. Aromatics also smell really good, by the way. That's where we get that from. The Wiley Plus plug again, check it out. Draw some resonance structures with 2.25. All right. So next we need to assess these resonance structures, right? And which is really interesting because really what we're doing now is we're going to figure out what the hybrid structure is, right? There's some rules for that too, but we did a lot of it in the previous slide, so this is mostly a review of what I said already before in the previous slides. But we really want to beat this into your head so you know how to do resonance structures, because if you can't do a resonance structure, you're not going to be able to do a electron pushing reaction, and that's what the rest of the semester is about. Okay. It's very much about practicing using arrows to push electrons. So here we go. Rule 1: the most significant resonance forms have the greatest number of filled octets, right? So what we mean here is that, remember, I was drawing resonance contributors, right? So when I have one structure and I know that it can undergo resonance, do resonance delocalization, right? Then I can draw another one that represents its other delocalized form, right? Both of those are resonance contributors, right? But remember what I said. I said that it's actually the structure is somewhere in between, right? So one structure contributes to that structure more, that in between structure more than the other, right? So we have rules now on how to determine which structure mostly contributes to the to that resonance hybrid that I was talking about, right? So take a look at this here, right? We have this structure right here, and we have an oxygen here with a carbocation. That carbocation doesn't have a full octet, does it? Right? That's why it's got a plus charge. It's missing an electron, okay? Whereas this over here, all right, this guy over here, every atom has a full octet, okay? This oxygen here has 1, 2, 3, 4 times 2 is 8, right? So that's a full octet. This carbon, right, though sp2 hybridized, has also got an octet, right? And none of the other guys that are part of the molecule are actually participating in the resonance. So the molecule, or the resonance structure contributor, that has the most full octets is going to be the one that participates the most significantly, or is going to be the one that represents the resonance hybrid more significantly. Okay. In rule 2, the structure with fewer formal charges is more significant. Well, that makes kind of sense, right? Because when you have fewer charges, that means they're not spread out on different areas of the molecule where there's a plus charge over here and a minus charge on the other side, right? Seems kind of weird. So taking a look at this guy right here, right? We have the least significant structure here in the resonance hybrid, or resonance contributors contributing to the resonance hybrid, is this structure here, in which you have a carbocation right there, right? Then you have a negative charge here on the nitrogen because it has an extra set of electrons, right? And then also, not to mention the fact that it doesn't even have all of rule 1, which is every atom has a full octet, right? The carbon doesn't have the carbon has a full, doesn't even have a full octet. So that's what makes this structure, this resonance contributor, the least likely or the least significant contributor. It's sometimes there, but it's not there very often. Okay. In number 2, this structure resonance contributor here is number 2 because while every single atom has a full octet, it still has formal charges at either side of the molecule, right? So then it leaves us with the most significant contributor to the resonance hybrid, which is this one. It has full octets for every atom, and then it also has the fewest formal charges, right? The fewest formal charges. So that's 2 rules right there you need to remember when it comes to determining what's the most significant resonance structure, right? Full octets and the fewest formal charges, and then you have to use them together sometimes, especially when you have multiple. When you have multiple resonance contributors. So here's another example of a rule 2, right? Turns out that all 3 of these are equivalent contributors, right? Why? Because each one has 2 negative charges, right? And each one has the same. Each one has the same octet rules being followed, right? Where carbon here is got its full octet, right? Then there's a full octet oxygen there, 1 full octet oxygen there, 1 full octet oxygen there, right? And then both of these oxygens on all of them that are single bonded are also full octets. So every single one of these atoms is a full octet, right? And they all have double negative charges, right? So these are all going to be the same contributor, right? It equivalently contributes to the hybrid resonance structure. What isn't is this resonance structure here, because holy crap, that's a lot of different charges, and that's a lot of no octets, right? This carbon here doesn't have a full octet, okay? But then we have 4 different charges over the span of the molecule. So even though this might contribute a tiny bit, tiny bit, right? It is not a significant resonance structure. Okay. Ooh, rule 3. A structure with a negative charge on the more negative electronegative atom, the structure with a negative charge on the more electronegative atom will be the more significant, and vice versa, right? And this makes kind of sense because remember, use this one as an example here. Oxygen loves electrons because it's electronegative, right? Carbon is not as electronegative, right? So the one that has the negative charge on it, and it's the more electronegative atom, will be the one that's the more contributing, which makes a lot of sense because really what's going to happen here, right? The electrons really on this carbon here, for this carbon anion right here, are going to be drawn towards the electronegative carbon anyway. I mean, electronegative oxygen anyway, right? So that's why this this right here, this structure right here is the most significant when it comes to the different contributors to the resonance structure. We default to rule 3 here because more than one structure has all atoms with a full octet and the same number of formal charges, right? So you need to use all these rules together. Here we go again. Oh my God, isn't that a song? That's a White Snake song, isn't it? Here we go again. Sorry. I don't want to get like a copyright infringement or something for talking about White Snake on a lecture video. Anyway, so again here, which one is the more significant? It's definitely going to be this one here because the charge, the plus charge here, is on the less electronegative atom here, which is the nitrogen, right? That's what the vice versa means, right? That's what the vice versa means, okay? And then another plug for Wiley Plus. Go over to Wiley Plus to do Skill Builder 2.8 for some help with drawing a resonance hybrid. Oh, finally, we're actually at resonance hybrids when we've been drawing resonance hybrids this entire time. Yeah, okay. The resonance hybrid represents the pi bond of an allylic carbocation as being delocalized over all 3 carbon atoms. Literally, that's what I drew for you in the very first slide, right? We have here the molecular orbitals, all the p orbitals overlapping, making the molecular orbitals such that they're spread out over the entire span of the molecule. And so when we draw the resonance hybrid, we want to be able to show, right, what the molecular orbitals reflect, right? And this one doesn't even show the one where the non-bonding molecular orbital here, where it's like this, right? Right, where they were, right? And that's why there was the carbocation on both sides, right? Carbocation on both sides. Whew, okay, let's keep trucking here. I feel parched today. Localized electrons are not in resonance, which we knew that already, right? It's only delocalized electrons that are in resonance, okay? Delocalized electrons are in resonance and are more stable, yes. To be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital. Okay, so we know this already. Okay, remember that we were talking about before with the pictures I had before, right? With the p orbitals like that on that allylic carbocation, right? And all these p orbitals right here are overlapping because they're not hybridized, because that was from an sp2 carbon, which left one p orbital left over, right? Left one p orbital left over, okay? And that one p orbital is what causes, that one p orbital is what makes the double bond, or the pi bond right there, right? And that's why those electrons can be delocalized throughout the entire span of the molecule with that molecular orbital, right? So the lone pair on this nitrogen is delocalized because it is next door to a carbon atom with a p orbital, right? Which we knew that already because we've seen this before, where these electrons can come down, go back up here like this, okay? And then so the structure you get, and I don't know why that my arrow just kind of fudged up there. There we go. Is going to be this. And for you biochemists out there, this should be a very familiar molecule or structure to you, because this is actually an amide bond, or more. Hold on 1 second here. Trying to get that in there. There we go. So it looks like that now. Actually, it's a little dirty. Let me draw that again for you. I'm gonna do it this way. There we go. Because I think I have a lot more room over here. Here we go. So that's the structure you get now. Okay. Oh, and I forgot to draw the. Just for your sake, I'll draw the lone pairs. Okay. Lone pairs, and that's the other resonance contributor to this amide right here. But an amide is also known as a peptide bond. Right. This right here is called an amide bond. That right there is called an amide bond. It's also known as a peptide bond. And it's the bond that holds all your amino acids together to make a string of amino acids, also known as a primary structure of a protein or enzyme, which gets folded up with hydrogen bonding and other different non-covalent interactions, right? Like hydrogen bonding and hydrophobic effect and all that stuff, to make the secondary structures of proteins, which are the alpha helices, the beta sheets. Those then come together now. Excuse me. Those then come together now to make, using more, non-covalent interactions like the hydrogen bonding ionic interaction, the hydrophobic effect, London dispersion forces, all come together to make the tertiary structure of a protein / enzyme, and that is the active form of an enzyme. Sometimes those tertiary structures even combine with each other, making a huge structure called a quaternary structure, and that's the active form. Like there's a super big enzyme I used to study called pyruvate dehydrogenase. It's part of sugar metabolism, right? Not glycolysis. It's actually the step right after glycolysis, the one right before TCA cycle, the citric acid cycle, and that thing is mother huge. Pyruvate dehydrogenase. You'll learn more about that later on in life, I suspect, because most of you are in this class because you're trying to go to med school or you're trying to get like some kind of professional science degree or something, so you'll have to take biochem and you'll learn all about proteins and enzymes. Okay? Anyway, that's very important. Next. Oh, my bad. It already drew it for you here. Why do I keep on doing that? I keep on drawing the structure before the actual structure comes up, right? In one structure, the N is... Oh, this is actually something interesting, something different. In one structure, the N is sp3 hybridized, and in the other, the N is sp2 hybridized, right? So notice in this one here, we have sp3 hybridized, right? Right, it's sp3 hybridized. Why is it sp3 hybridized, that nitrogen? Is because you have 1, 2, 3, 4 electron domains. Gives it a steric number of 4, which means it's sp3 hybridized. And then over here we have 1, 2, 3, steric number 3, sp2 hybridized, right? So the question is, what is it? Is this structure sp3 hybridized or sp2 hybridized, right? Well, if a lone pair participates in resonance, then it occupies a p orbital, right? So the lone pair is delocalized, which is only possible through the overlapping p orbitals, right? Remember, they're overlapping p orbitals here to make that double bond, right? So that the double bond has to be there, right? Or the p orbitals have to be there to form the double bond, to form the pi bond, right? So that must mean then that the nitrogen is sp2 hybridized, right? It's not actually this single bond that we see over here, right? It must be sp2 hybridized. Good times, good times. Okay, so let's take a look at this guy right here. This guy right here is named pyridine, right? This guy right here is named pyridine. And pyridine looks like it actually follows one of the rules, which is a lone pair, right? Right next to a allylic carbon, right? Or a double bond, right? Lone pair next to a double carbon with a double bond, or a allylic lone pair, right? It looks like it. It looks like it's adjacent. That's what I was looking for. A lone pair adjacent to a double bond, right? It looks like that. But the problem is that this lone pair, it's actually a localized lone pair, right? It's a localized lone pair, which means that it's not going to be participating in any kind of delocalization or resonance. But how do we know that, right? Well, we know that from two different ways. One way is that when we draw out the molecular orbitals here, right, we see that there are p orbitals already around on all these different carbons and the nitrogens of the pyridine, right? And we know that they're there because there are double bonds here, right? Those double bonds wouldn't be there if there weren't p orbitals there to overlap to form a pi orbital, a pi bonding molecular orbital, right? To form those double bonds, right? So since these p orbitals are already being used in the double bond system of the pyridine, that means then that the lone pair of electrons is actually stuck in a hybridized sp orbital, right? It's stuck in a hybridized orbital, right? Which one is it? sp2, right? It's stuck in a hybridized sp2 orbital, right? So if it's stuck in a hybridized sp2 orbital, then it can't participate in the delocalization, because it has to be a part of the overlapping p orbitals to make that entire conduit of p orbitals and pi electron / pi molecular orbital orbitals that are spanning the entire thing. So a fast way to actually identify the fact that this lone pair probably is not going to be participating, or any lone pair for that matter, a fast way to determine whether or not a lone pair is participating in delocalization or resonance, right? Even though it seems to be following one of the rules, in this case, the rule of adjacent double bond to a lone pair, right? Even though it follows that rule, how do you know whether or not it's, going to be delocalized and do resonance, is the fact that when you look at the molecule and the lone pair in question is on an atom that's already participating in a double bond, right? And if that atom is already participating in a double bond, that means that p orbital that made that double bond is already being occupied, being used to make the double bond, right? So that lone pair must be in a hybridized orbital, right? It must be in a hybridized orbital. Everybody got it? Good stuff. So, some general rules here, okay? Just so that you can be clear about these things. Don't assume that a lone pair is delocalized just because it's next door to a pi bond. It's this thing I just told you in the last slide, right? As a general rule, you can assume that when an atom possesses a pi bond and a lone pair, they both will not participate in resonance, right? And as always, if there is no p orbital next door to a lone pair, then it will be localized, right? So, just a quick look here. We have a delocalized lone pair right here, right? Okay, because this nitrogen right here is not participating in any double bonds. There's a lone pair there, and it's also adjacent to two pi bonds right there. But you do have a lone pair there, and it's adjacent to a pi bond right there, but it's a localized lone pair. Why? Because it's already participating in a pi bond over here, right? So this guy, these two lone pairs over here, this lone pair over here, is in a hybridized orbital. It's not in a p orbital, okay? And then here, obviously, This is definitely a localized lone pair because you're not surrounded by anything that is a part of that rule. Those rules that we were talking about, right? So I think that actually ends this lecture. I was right. That ends today's lecture. So due by tomorrow, 7 a.m., 7:59 a.m. That's June 4th, 2021. Quiz 2 and your molecular representations assignment, right? And then again, the reminder here is on Friday, which is tomorrow. You also have an exam, right? Good luck with that. I'll see you in a few minutes for your pre-lab lecture.